Hello, welcome to this lesson on the states of matter. We will be reviewing what I assume you've learned in the past about the states of matter, solids, liquids, and gases, and we will go a little bit more in detail, I hope, and expand your knowledge by focusing on the molecules and atoms that make up the substance when they're in those various states and how those molecules or atoms are behaving. We will use the term states of matter or phases of matter interchangeably. States and phases mean subtly different things to scientists, but most often those words are used as if they mean the same thing. I am assuming that at some point in the past you learned that solids have a fixed shape and volume. When we use the word fixed, we mean definite, unchanging. So we see this small blue cube represents the solid in a larger clear container. The solid is holding its shape. It's not taking the shape of its surrounding container, and it's holding its volume. It's not expanding to fill up the extra space of the container or being smashed into a smaller container. Solids have fixed shape and fixed volume, or sometimes we use the word definite shape and definite volume. Liquids have fixed volume, so if I have 200 mLs of liquid and pour it into this cube container, it will take up the shape of the cubed container in the bottom. If I were to pour it into a cylindrical container or a spherical container or an Erlenmeyer flask, something with a different shape than we see here, it would occupy that different shape. But it would still be 200 milliliters. It would still have its same fixed volume. Gas molecules expand to fill whatever size or shape the container is that they are in. So they do not have a fixed shape or a fixed volume. They can expand to fill up a bigger space. They can be compressed to take up smaller amounts of space. They take up whatever shape the container has. Solids have fixed shape and volume. Liquids have fixed volume, but not fixed shape. And gases do not have fixed volume or fixed shape. That is what I am assuming you already know. Our lesson is going to be about how the particles that make up a solid, liquid, or gas are behaving. And a solid, liquid, or gas will be made up of particles that depend on what that substance is. So if that substance is an element, like sodium or iron or sulfur, we would typically call those particles atoms. And if that substance is a compound, like water or carbon dioxide, then we would typically call those particles molecules. So I will be using the term molecules if it's a compound. I will be using the term atoms if it's an element. I will be using the term particles if I mean something more general. I'm not specifying. The particles of a solid, particles of a liquid, the particles of a gas are behaving differently to give the solid, liquid, and gas its properties. They're bonded differently, their motion is different, and that's what we want to focus on. Here we have images of the 3 or 4 traditional phases or states of matter that are well understood and commonly found on Earth. We see these ice sculptures representing water as a solid. We see a drop of water bouncing back out of the liquid in the liquid form of water, and at the bottom on the left we see water vapor in the form of clouds, and in the bottom on the right we see an electrical discharge that must be creating a plasma in the gas that surrounds it. We'll talk a little bit about plasmas as we move through the lesson today. These are not the only states of matter. There are other states of matter than these 4, but these are the most common and the ones that we are most familiar with, the ones that we understand the most. We'll be talking about plasmas a little bit as we continue, and at the end of this lesson I have some references for you if you'd like to look up some additional information about plasmas or some additional information about a state of matter that was most recently created in 1995 called a Bose-Einstein condensate. So that's a fifth state of matter that scientists are investigating. All right, so we want to go beyond this idea that solids are materials with fixed shape and fixed volume, and liquids are materials with fixed volume but not fixed shape, and gases are materials without fixed shape or without fixed volume. We want to talk about what the molecules are doing. In order to talk about what the molecules are doing, I'd like you to read the information underneath these images. I will hit some highlights, and then I will also be adding to it with some additional information. So, what can we say about solids? In a solid, the molecules are arranged in a regular way. They typically have a pattern to their arrangement. They're held firmly in place because they feel strong molecular attractions. So there are attractions between these atoms and molecules that hold them firmly in place. They can't move around a lot, but they can vibrate in the positions that they are in. The molecules are close together, so they can't be compressed further. The molecules are close together, and so they typically have high density. The molecules have very little freedom of motion. In a liquid, the molecules feel less strong forces of attraction. I probably could say that more clearly by using the term weak. In a liquid, the forces of attraction between the molecules are weaker. The molecules are generally farther apart in a liquid, making the liquid typically less dense than the solid, although that's not always the case. There are fewer bonds between the molecules of a liquid. So the molecules of a liquid might be bonded to some of their neighbors, but not all of their neighbors. And so if the molecules of a liquid are bonded to just some of the neighbors, but not all of the neighbors, they can move more freely. They can rotate past one another, and this allows liquids to flow in a way that solids cannot. They feel weaker forces of attraction, they have fewer bonds, there's more freedom of motion. Molecules of a liquid can rotate in ways that molecules of a solid cannot. So molecules of a solid are just sort of stuck in place, vibrating back and forth and back and forth and back and forth. Whereas molecules of a liquid, they can do that vibrational type of motion that solids can do, but they can also spin. And that spinning, that rotation, gives them an additional type of freedom of motion. Molecules of a gas feel very, very, very weak forces of attraction for one another. They're so small that we basically ignore them. In fact, we have a very important theory about the motion of the molecules of a gas that says the molecules of a gas do not feel forces of attraction or repulsion for one another. That's probably not the case in reality, but at very, very high temperatures, the molecules are moving so quickly that they overcome those forces of attraction very, very easily. So we ignore them. The forces of attraction between gas molecules are insignificant or negligible. There are big spaces between the molecules. The molecules have virtually no bonds between them. You see some molecules might be bumping into one another, but they're not really bonded. They're not stuck together. They're going to bounce away from one another in just a moment. And the molecules of a gas, because they're very far apart, show very, very low density. In addition to being able to vibrate and rotate like the molecules of a solid or liquid can, molecules of a gas can also have a type of motion that we refer to as translational. And this means that the molecules can move from place to place. So at one moment the molecule is here and it literally moves to a new position somewhere else. It goes through a displacement. And the molecules of a liquid and the molecules of a gas can't really do that because there are too many other molecules in their way. And so molecules of a gas have much higher degree of freedom than the molecules of a liquid. Because the molecules of a gas are so far apart, the molecules of a gas are compressible. And what that means is that we can move them closer together by putting them into a container with some kind of movable wall. So if I have a container with a movable wall like this, that's typically called a piston, I can push the piston down, and when I push the piston down, it will take up some of the space between the molecules, and the molecules will just be closer together than they were before. But they will still be in the gas phase. So we can compress the molecules. Molecules of a solid, molecules of a liquid are not very compressible. We refer to these states as condensed forms of matter. So they're already about as close together as they're going to get, the particles, I mean, and so we can't smash them together further. Let's take a moment to look at a simulation where we can actually see the molecules in motion rather than these pictures that aren't allowing us to see the vibrational and rotational and translational motion of the molecules. So this is an image of a container that has within it solid oxygen. So you can see over on the left I've clicked in front of oxygen and I've hit the button for solid. Up at the top you see a thermometer that reads the temperature, -242. This is below the freezing point of oxygen. So the oxygen is in a solid state. Oxygen is diatomic, so each of the molecules has two pieces. Two little red balls make one oxygen molecule. And you can see that in the solid, the molecules have very little freedom to move around. They can basically vibrate. If I cool them, here I see this big clump of ice coming out to cool them down, and you can see up at the top the temperature is dropping, getting closer and closer to -273, which would be absolute zero. And as the molecules are being cooled, you can see that they slow down. Their vibrational abilities are limited, more limited at the colder temperature. So what is temperature actually measuring? It's measuring the kinetic energy of the collection of molecules. So on average, the kinetic energy of these molecules is lower now because I lowered the kinetic energy, which means they're moving more slowly. They could only vibrate before. They can only vibrate now, but they're vibrating more slowly. And as I heat them up, now we see the temperature rising. We can see the molecules have greater vibrational motion. So on average, they have more kinetic energy, more motion. If I heat this beyond the melting point, we'll see the structure of the solid break down. And so here I have liquid oxygen. And so the molecules are still connected. They feel some forces of attraction for one another. You can see them both vibrating and rotating. Sometimes the molecule will escape and get out into the gas phase. If it slows down, it can rejoin the liquid phase. I'm above the melting point now. If I heat it further, I will see that the molecules will be vibrating and rotating so quickly that they will break the rest of their bonds. And when all of the bonds are broken and the molecules are moving around separately and freely with high degree of motion, then I can see that obviously we are in the gas state now. Big spaces between the molecules. The molecules are still vibrating, they're still rotating, but now they have the ability to move from one location to another very, very easily because there are such large spaces between them. In fact, they move as, you know, the law of inertia would say they move. They move forward at a constant speed until they bump into something, and that changes their direction. So they move forward until they bump into another molecule or until they bump into the wall or whatever. And I can do this backwards by cooling the molecules down, and that will slow them down as the temperature drops, their kinetic energy drops, and they move more slowly. And eventually, when I get to the point at which they condense, we could call that the condensation point or the boiling point. I just passed it. It was negative 183. And now I have liquid oxygen. And if I get this even colder, if I go down below negative 219, that's the freezing point of oxygen, I'll get back into the solid state. Okay? So molecules vibrate, rotate, translate more if they are at higher temperature and less if they are at lower temperatures. I get to a certain temperature where the bonds are breaking to go from solid to liquid, and when I get to another temperature, the rest of the bonds will break when I go from liquid to gas. Let's quickly review the phase changes that we spoke about last week when we were talking about physical and chemical changes. As I go from a solid to a liquid, I refer to that as melting. Bonds are breaking. As I go from a liquid to a gas, I refer to that as boiling. Again, bonds are breaking. And I have to add energy to break bonds. Energy is going into the molecules, giving them additional freedom to move around. If I go from solid directly to the gas state, we refer to that as sublimation. And we grouped those three phase changes together. We said for all three of those, bonds are breaking, energy is needed, added to the molecules. Since heat is going in, we refer to them as endothermic. Here we see an image that's showing the plasma state. The plasma state is like the gas state in that the particles have large spaces between them and high degree of freedom of motion, but the particles are charged. When we get to the plasma state, the actual atoms have started to break down. The gas is so energetic that the electrons are actually being stripped off of the atoms. And so as the electrons come off, what they leave behind is positive. So the larger orange or yellow pieces are positive ions, and the small little purple pieces are the negative electrons that have been stripped off of those positive ions. So a plasma is like a highly charged gas. Plasmas exist at really, really high temperatures like the surface of the sun, tens or hundreds of thousands of degrees Celsius. The state, what we call the change from a gas to a plasma, is ionization. When we are removing electrons from atoms, we are creating ions, so we call that ionization. And when we go backwards and put the electrons back on the atoms, that is referred to as electron affinity. A love of electrons, a desire for electrons, electron affinity. The phase changes that are the reverse of the endothermic phase changes are exothermic. So when gas molecules form bonds to make a liquid, we call that condensation. And forming bonds releases energy. And when liquid atoms or molecules form bonds to become a solid, again, energy is released. If the gas molecules go directly to the solid state, we refer to that as deposition. And these phase changes all show bond formation. Energy is being removed from the molecules. You have to take energy out of the molecules in order to get them to form these bonds. They release energy when they form bonds. Heat is coming out, so we refer to them as exothermic changes. And you should understand them as a group as well. All right, that's a review of what we did last week. Very quickly, couple of little last minute things and then we will be done. Liquid to gas. When a liquid changes to a gas, we actually have two names for that process. One is evaporation and the other is boiling, and you should understand the difference between those two things. It's fairly simple and obvious, actually. Evaporation occurs for molecules at the surface. So at the surface of the liquid, there are some molecules that have enough energy to escape. They're bonds with the rest of the liquid. And if they break those bonds and escape from the bulk of the liquid and get out into the gas state and float around separately, we refer to that as evaporation. And evaporation occurs at any temperature as long as the substance is a liquid. Boiling, on the other hand, occurs everywhere at once. It occurs throughout the liquid. It doesn't just occur at the surface. So if I have a bunch of molecules over here that have enough energy to get into the gas phase, they will form a bubble of gas, and then that bubble, because it's less dense, will rise to the top and burst open and release those gas molecules. But it doesn't have to happen at the surface. It can happen anywhere in the liquid, and if something is at a really big rolling boil, then you have bubbles forming all over the place and rising to the surface, bursting open to release the gas. So boiling occurs throughout the liquid, not just at the surface. And boiling occurs at a specific temperature that we refer to as the boiling point. Now, boiling point's not actually a constant value. It's dependent on how much pressure is pushing down on the liquid. You don't really need to know too much about that. I feel like I spelled specific wrong, and I need to go back and fix that. And whereas evaporation can happen at any temperature, you know, if I leave a beaker of liquid out on my desk and it's just at 20 or 25 degrees Celsius room temperature, I might come back 3 days later and it will be gone. It will have evaporated at that lower temperature, and the temperature may have varied in the room, and evaporation was occurring all along. Boiling occurs at a specific temperature when all of a sudden all of the molecules in the container have enough energy to get into the gas state. Evaporation is a cooling process. It's a cooling process because the molecules left behind have less energy. And so I have a quick simulation of that. I have some images from that simulation which you can take a look at later, but let's look at the whole simulation now. If I run the simulation, what's represented here is a container of liquid molecules. Look over here on the right-hand side, and you can see the temperatures hovering around 270 degrees Celsius. There's a cover on this, so no evaporation is occurring. If we remove the cover, and some of the molecules at the surface can get out into the gas phase, and we can see over here in this little purple box the number of molecules left. So I'm at 109, 108, 107. Molecules are leaving the liquid. Well, look, the molecules that are left, they're the slow ones, because the fast ones are able to escape. So if the collection of molecules that's left, I'm going to stop this for a second, if the collection of molecules that's left is the set of molecules that didn't have enough energy to escape, then in general, their average kinetic energy is much lower. So look what happened to the temperature. The temperature of the solution that's left over, the temperature of the liquid that's left over has dropped because all the high-speed molecules are the ones that are left, are the ones that escaped, and so the average kinetic energy of the leftover molecules is dropping because all the high-speed molecules are leaving. And so the average kinetic energy of the molecules that are left over is dropping, and so you can see that the temperature has gone down from what was about 270 to what is now about 120. All right, so evaporation is a cooling process because the leftover molecules have less energy as the high-speed molecules escape. If you are in a nice, warm, heated pool, but you get out of it and it's kind of a chilly day, the evaporation of the water, the liquid water, off of the surface of your skin is going to leave you feeling colder because the molecules that are left over have lower average kinetic energy. And also, the molecules are stealing energy from you so that they can get out into the gas phase. And if they're taking some of your energy, you're going to feel colder. Finally, states that we are less familiar with. Plasma is like the gaseous state, only particles are charged. So examples of plasma would include the air around a lightning strike. There's enough energy from that lightning to strip electrons off of the oxygen or nitrogen molecules and create a plasma. Inside a tube of a neon gas light, the gas is highly energized and highly charged. I'm sure you've seen those kind of fun plasma balls where, again, there's kind of an electrical discharge coming from the center and the gas in the ball is ionized. And here they're showing the reentry of the space shuttle into the Earth's atmosphere, and behind the space shuttle, the gas is superheated, and so you can see a plasma trail behind it. Plasmas occur at super high temperatures. I know that we said that changes of state were physical changes and not chemical changes, but the change to a plasma could not be considered a physical change. If I had water, for example, and tried to raise its temperature to 10,000 degrees Celsius, it just would not be water anymore. The water molecules would first break down into hydrogen and oxygen molecules, and then the hydrogen and oxygen molecules would break down into hydrogen and oxygen atoms, and then the electrons would start to come off of those atoms. So by the time I got to this high temperature, there's no way it's water anymore. So that would not be considered a physical change. And that's a little confusing because we say changes of state are physical changes, but then if we want to include plasma as one of the four states, that gets a little bit confusing because that couldn't possibly be true, that the change to a plasma was just a physical change. And then finally, if you're interested in some more information about plasmas or this new strange state of matter called a Bose-Einstein condensate, then check out chemforkids.com. I know that sounds kind of hokey and stupid, but it actually is a really good site, and I thought that the information that they had about Bose-Einstein condensates was pretty interesting, and there was a good video on that site as well, describing Bose-Einstein condensates, and here describing plasmas. I like the Bose-Einstein condensate one a lot. What happens at very, very cold temperatures, that is billionths of a degree Kelvin, and by that what we're saying is we're just barely above absolute zero, so 1 over 10 to the 9th degrees Kelvin. You don't really put the degrees symbol in when you talk about Kelvin. Anyway, when you're at these super, super cold temperatures, the atoms are almost still. There's so little kinetic energy left that the protons, neutrons, and electrons of the atoms are almost motionless. And apparently, at those cold, cold temperatures, the atoms kind of superimpose on one another and make kind of super atoms, like a blob of atomic stuff. They stop being discrete and separate atoms, and they kind of turn into one big atom. I know I'm not explaining it very succinctly, but check out that video. It's kind of interesting. All right, very good. a review of states of matter and hopefully some new information for you about what the molecules are doing, how they're moving, how they're connected to each other.